Good. So we were talking last time, as I said, about the structure and nomenclature of alcohols. Today, I want to get more into the properties of alcohols, including their acid-base properties. And then as well, maybe we'll begin to scratch the surface and go over a few reactions that alcohols can undergo. And I think that will be enough for today. We can leave most of the remaining reactions for Wednesday. And then the plan is on Friday to start chapter 8. Chapter 8 will not be on exam number 3. That will be on exam number 4. So like I said, the syllabus talks about exam 3 and puts it on the schedule a week from today. And we should have no problem doing that. I've left Friday as a slop day, as I call it, as I like to do, just to make sure we have enough time to finish all the material. And in case there's some reason that we have to lose a day of class, then we don't have to move the exam also. Good. So reminder about hydrogen bonding. Hydrogen bonding is one of the intermolecular forces you learned about in Gen Chem. And in many ways, it's the most significant intermolecular force, at least if it's there. And you'll recall that we know that hydrogen bonding is there for compounds that have either OH or NH bonds anywhere in their structure, OH or NH bonds. The hydrogen has to be directly connected to either oxygen or nitrogen, or fluorine is the third one, yes, but once you connect a hydrogen to a fluorine, you're done. Both atoms can form only one bond. So HF is another molecule that exhibits hydrogen bonding. But it seems to need to be an atom that's both very small and very electronegative in order to have any significant degree of hydrogen bonding. And I've read some rumors here and there of a teeny bit of hydrogen bonding in thiols, but you're talking just a trace. I think someone had to try really hard to detect that. Certainly for our purposes, we're only going to find hydrogen bonding of any significance in compounds that have OH and NH bonds. Those are going to be the ones we'll need to look out for. So you're talking alcohols, you're talking carboxylic acids, certainly, and you're talking primary and secondary amines, which we talked about in chapter 11. Those are going to be the main times we're going to run into any significant degree of hydrogen bonding. And so let me just remind you of what that looks like. Remember, we call these intermolecular forces. That means that they're forces felt between and or among two or more molecules. And a hydrogen bond is an attractive force that's weaker by far than a covalent bond, but certainly detectable, that we find between the oxygen in one alcohol molecule and the hydrogen in another alcohol molecule. And so it means that they're going to line up or order up to some degree, forming kind of a network, if you will. And these are obviously always shifting, and you might break one hydrogen bond and form another. But you would get something that looks kind of like this, and of course this oxygen would in all likelihood find the hydrogen in another alcohol. But I just wanted to make sure that you guys had some kind of visual aid as to what hydrogen bonds look like. And I may be being a little sloppy. I should probably have drawn all of these alcohol molecules as being bent. Well, that can be easily rectified, right? There, that's better. So something like that. That's what I'd like you to be thinking about when you think about hydrogen bonding. And so I'm representing the hydrogen bonds as dotted lines. Please do be aware that these are not covalent bonds. Again, that's why we call these intermolecular forces, because they're between any two molecules. And so alcohols have the ability to undergo hydrogen bonding. We could do that several hundred more times if we wanted to. I don't think we do. I certainly don't feel like drawing several hundred more of them. I think you get the idea. But in the bulk state, this is going to be what an alcohol looks like in the liquid state. And so because of that, that means that in order to get the alcohol, for one thing, to go from a liquid to a gas, in other words, in order for the alcohol to boil, we need to disrupt these hydrogen bonds. And that's going to take some extra energy as compared to what you would find if the hydrogen bonds weren't there. If we compared it to a similar molecule of similar molecular weight, for instance, let's see, methanol is CH3OH, CH4O, that's 16, and another 16 makes 32. So what would be an alkane of similar molecular weight? Would ethane be C2H6, 14 and 6 more is 30. Yeah, 30 versus 32, that's pretty close. I think we're pretty much comparing apples and apples here. So ethane is about the same molecular weight as methanol, which is when R is a methyl group over here. But I'm sure if you looked up the boiling points, the boiling point of ethane is going to be stupidly low. It's going to be probably like minus 80 or minus 100 degrees Celsius. Whereas the boiling point of methanol is a great deal higher, much higher than you would guess just for having 2 more AMUs in its molecular weight. Methanol, I should know these things off the top. I feel it's like 58, 60 something, maybe high 50s, low 60s Celsius. You can double check me on that, and I don't care if you memorize those numbers. But my point is, you're going to see, I would expect, again, I don't have the numbers memorized myself, but I would expect you'd find a difference of over 100 degrees in the boiling point of the two. Ethane is certainly a gas at room temperature, and you'd have to cool it down to something ridiculously low, as I said, in order to condense it into a liquid. Methanol is a liquid at room temperature, and it's not even close. You know, you'd have to heat it up to around about 60, I think, in order for it to boil. So that's mostly, if not entirely, because of these hydrogen bonds. We have to put in energy in the form of heat in order to disrupt those hydrogen bonds. And so that's why you find these differences in properties peculiar to alcohols, as opposed to other molecules of a similar molecular weight, let's say. What else was I going to say about that? Oh, one last point on hydrogen bonds. Does hydrogen bonding also increase melting point? Excellent question. I think, let me think now, because we have to be careful. Wasn't there, oh no, I'm confusing it with mole freezing point depression. That's a different critter. That's talking about solutions. So in that case, I think the answer to your question is yes. I would expect it also to increase melting point, other things being equal. But you know, you would have to, even the melting point of methanol is going to be minus 80 or something. So you would want to get larger molecules before you find higher melting points that at least are worth considering, I would think. But my one-word answer to the question would be yes. I would expect it also would increase the melting point. It would also increase viscosity, by the way. Viscosity is defined as resistance to being poured. So you know if something really viscous might be maple syrup or ketchup or something like that. You know, you can get quantitative about viscosity. I forget what the unit is, but you can measure viscosity. And I'm sure if you measured the viscosity even of methanol and you compared to something without hydrogen bonding that's similar, I wouldn't be shocked if you found methanol was more viscous, though it doesn't particularly resist pouring very much. You know, pouring methanol doesn't look very different from pouring water. But these things that stem from effects on the molecular level do have real effects in the world we inhabit. That's mainly the point I want to make, and the point that I hope your Gen Chem professor also made. But of course I wasn't there. Last point I want to make on hydrogen bonding, and it's a subtle one, but it's one that I've learned over the years I need to stress very heavily. I especially learned this when I was teaching Gen Chem. You need to be aware that when you put in energy to disrupt these hydrogen bonds, so to boil the alcohol, let's say, please be very clear that we are not breaking any covalent bonds when we boil a compound. Whether an alcohol or water or anything else, we are not breaking any covalent bonds. This is only a physical process. We're not breaking any, we're not changing the structure of the molecules. We're just disrupting these intermolecular forces. And I guess my point is, and I really didn't expect to riff on this for so long, but sometimes I amaze even myself. But I guess my point is that since we need to put in extra energy to disrupt these hydrogen bonds, that leads to observable effects. Even though hydrogen bonds happen in the submicroscopic world of the molecular level, they have real effects that we can observe in everyday life. So I think with that, that's about all I need to mention. Yeah, I have a little bit more on that in the class notes, but I thought this was a good time to review hydrogen bonding. But please do be aware they're intermolecular forces. They're not covalent bonds, completely different critters. Good, hopefully fairly straightforward, hopefully ringing a bell from Gen Chem. We also covered this in chapter 2. So if you need some more review on that, you can feel free to go back and look at chapter 2. But section 7, I think, yep, 2.7. So if you need to, that's fine. Good. So I sort of squeezed 3 or 4 sections of chapter 5 into one section of your class notes, since there's several of them that are talking about acidity. And we've talked about acidity and basicity before. I think we refreshed our memory on pKa's, that we generally use pKa, which is minus the common logarithm of the Ka, which is Ka is the equilibrium constant for, or the acid dissociation constant, I would say. But we normally like to use pKa rather than Ka. There's nothing wrong with using Ka values. It's just that Ka values are kind of a pain. And I don't expect you to memorize any of those numbers, certainly. But if you look at a typical Ka value for any organic acid, it'll be some silly number like 5.41 times 10 to the minus 13. You know, they're just not very, they're not very helpful numbers. They will always have scientific notation like that. And when you take minus the common logarithm, minus the base 10 logarithm, you get this nice number like 6.93 or 15.8 or something like that. And it's just much easier to deal with that. So that's the reason we use them. I guess if you had to memorize or almost memorize one pKa value, if you had to do one, probably a good choice would be water. It'd be really good if you knew that water had a pKa in the upper teens, around 16, thereabouts. And indeed, we find that, wait a minute, I want to make sure, is hydrogen bonding in alkyl groups, same as in, there's not going to be any hydrogen bonding in a hydrocarbon, right? Because you need the hydrogen attached to an oxygen. So you're not going to have any hydrogen bonding in alkyl groups. You can get some degree of dispersion forces or van der Waals forces, but you're not going to have any hydrogen bonding unless there's OH bonds or NH bonds. And so that leads to the differences that we were going over in terms of properties of these molecules. Good. At least, is that what you meant? Did I interpret that right? I think that's what you meant. So we only look for hydrogen bonding in molecules with OH bonds or NH bonds. That's the only time we run into it. Good. So let me see. So if we have down that water is, round about 16, I would say most aliphatic alcohols, again, where R is an alkyl group, most of them are a little bit less acidic than water. By a little bit, I mean 1 or 2 orders of magnitude, which actually is kind of a lot when you put it that way. But I think if you look up pKa values, which again, I don't care if you memorize them, but if you looked up any pKa values for methanol, ethanol, propanol, isopropanol, I think you'd find them to be in the upper teens, around and about 18, 17, 18 is pretty typical for aliphatic alcohols. So they're slightly less acidic than water. What that means is, well, what is the conjugate base of water? Of course, the conjugate base of water is OH minus, right? You just take away a hydrogen and add a minus charge. So what that means is the hydroxide ion, since it's the conjugate base of water, is not going to be a strong enough base to deprotonate most alcohols in any reasonable quantity. The equilibrium would favor the alcohol and hydroxide ion. So maybe, actually, I'm sort of thinking on my feet here, but I think I can clarify that a little bit. Let's say we're considering an equilibrium like, methanol. I could have taken ethanol or any other aliphatic alcohol plus hydroxide, and let's consider the equilibrium. So I'm really doing equilibrium here, not resonance, right? But let's consider the equilibrium between that and the conjugate base of methanol, which is methoxide ion, CH3O minus. and water. And yes, I know you did these in Gen Chem till they were coming out your nose, your ears, etc. But we could consider this equilibrium. And I think what you would find is the equilibrium lies to the left. It favors the starting materials. This means that hydroxide isn't a strong enough base to deprotonate methanol or really any other aliphatic alcohol in any reasonable concentration. You might get a little bit of these two. Okay, you probably will get a little teeny bit of these two things, but 99.9+% of the molecules are going to remain over here like this. And at any given time, one hydroxide ion, one lone hydroxide ion somewhere will pull off a proton from methanol. And similarly, the methoxide ion that you get will find a water molecule and go back to this, but only the barest minimum concentration of these guys is going to be there at any given time. The equilibrium will heavily favor these two things. So that's the sort of thing that pKa's can really help you with. If you know, for instance, and I'm just using round figures, that the pKa of water is, let's call it 16. And the pKa of methanol, again, I'm talking very roughly here. I really should use like approximately equal over here. And if this one is, let's call it 18. Well, what that means is that water is a stronger acid and methanol is a weaker acid to the tune of about 2 orders of magnitude. Again, I'm using very round figures here. So what that means is water is the stronger acid, methanol is the weaker acid. And remember, the equilibrium always favors the formation of the weaker species, the weaker acid. And that makes sense. It's not going to favor formation of the stronger acid because the stronger acid is more reactive. So the equilibrium will lie mostly in this direction. And we could back out of these pKa values, the Kas, and if we wanted to, we could figure out the equilibrium constant of this equilibrium as written. I don't think there's anyone here really interested in doing that, and I might be a teeny bit, but not enough to actually do it. However, I'm confident that if we did go ahead and figure that out, I'm confident that as written, the equilibrium constant would be well under 1, very far under 1. I would be shocked if it was much more than 10 to the minus 5 or 6 or something like that. So that's the sort of thing that you can tell by comparing pKa's of two different substances. So that's the case for aliphatic alcohols. Now, phenol is a different critter. Phenol itself, as I recall, is a pKa of around and about 10, maybe 9.5. And actually, if we wanted to, we could set that up. What if we treated phenol with hydroxide? We can ponder this equilibrium. And then on the other side, you'd get the phenoxide ion. This was just pure dumb luck, but it looks like I really planned this very carefully, but it's actually going to turn out fairly well, I think. So you would get the phenoxide ion, which is the conjugate base of phenol, and you would get water by doing this. So again, let's call water, let's say it is a pKa of round and about approximately 16. It's probably a pretty good guess. 15.8 sticks in my mind. 16 is close enough. And phenol, I think if you look it up, the pKa is 9 something, but let's just for argument's sake, say it's round and about 10. Well, now phenol is the stronger acid. And so remember, these acid-base equilibria favor formation of the weaker acid. And now water is a weaker acid by quite a lot. Remember that the pKa scale is logarithmic. So it's not just like, not quite twice as acidic. This is going to be, this is going to be about 1,000,000 times as acidic as water. It's 6 orders of magnitude, right? Each notch in the pKa scale is a factor of 10. So phenol is about 1,000,000 times more acidic than water. So that means now the equilibrium is going to lie very heavily to the right, much more heavily than this one lay to the left, by the way. So, and like I said, we could put numbers to that if we really wanted to. I don't think it's reasonable for us to go there here in this class. Since weak acid gives strong base in reaction, so would CH3O minus be strong base in first reaction? Right, I would say CH3O minus is a stronger base than hydroxide ion. Likewise, I would say OH minus is a stronger base by a lot than the phenoxide ion. So, but the equilibrium will always, with no exception, favor formation of the weaker acid, That's just a general idea that I think we covered earlier, but I don't want you just memorizing that sentence. It makes sense. Of course, the equilibrium will favor forming the weaker acid. It's not going to favor forming the stronger acid. The stronger acid wants to get rid of the proton more. So it makes sense you're going to favor formation of the weaker acid. So now this equilibrium will lie almost entirely to the right. And in fact, you don't even need to go as far as hydroxide to deprotonate phenol. You can use much weaker bases than hydroxide. You could probably get away with using something like the carbonate ion, CO3 minus. You could use sodium carbonate. And if you added sodium carbonate to a solution of phenol, I guarantee you will pretty quickly see bubbles of carbon dioxide gas, which comes about from the carbonate ion being protonated. You get at first carbonic acid, H2CO3, which is pretty unstable. That's in your soda, by the way, or Coca-Cola, or whatever it is you're drinking. And that's what makes all the bubbles in there. But H2CO3 is pretty unstable. It winds up making water and CO2. It tends to form those two things. But I guarantee you would see those bubbles pretty quickly. And they would be of carbon dioxide gas, showing that the carbonate ion is reacting with phenol. So you don't even need to go nearly as far as hydroxide in order to pull off the proton from phenol. The only question that then leaves is, why? Why is phenol some 1,000,000 times more acidic than water? And for that, we need to consider the structure of the conjugate base of this phenoxide ion. So I'm going to clear this for now, and I'm going to redraw that phenoxide ion, or that conjugate base of phenol. I'm going to use the Kekulé structure now instead of the circle thing. And it's been said that the answer to almost any question you can ask in organic chemistry, if you say resonance or the inductive effect, there's like a 90+% chance that one of those two will be the correct answer. And in this case, you could even almost argue it's both, but in this case, resonance is the correct answer. So the phenoxide ion is a resonance stabilized species. And since it's not like I don't have time, let's see if we can find all the other resonance forms. I think there will be 3 other resonance forms. One of them will look like this. And we'll put a minus charge on this carbon. There's going to be another one that looks a little something like this. And if you're bored, see if you can think ahead as to what the other 2 resonance forms will look like. This is not a minus sign over there, by the way. That was just a dot that got a little ahead of itself. And there's going to be another one with the minus charge over here on this carbon. And last but not least, there should be one more, and I would anticipate that would have the minus charge. That looks pretty awful. Yep, it should be over here. And the double bonds will be here and here. So again, let's not lose sight of what resonance means. Resonance is not an equilibrium. Resonance is a phenomenon whereby we have more than one correct way of distributing all the electrons without moving any atoms. Remember, you're not allowed to move any atoms or turn the molecule or anything like that. You have to leave all the nuclei in the same place. And if you find, like in this case, that there's more than one way to distribute the electrons, then you've got a situation in which there's resonance. And what resonance means is not that it's, it's not that this minus charge is flying around all over the place and moving really fast between all those positions. Not at all. It says that this anion has one structure. There is one true structure of this anion. But using our normal valence bond model for drawing structures, we can't adequately represent that structure all at once in one structure, not using regular structure drawing conventions like we're used to. So we need to understand that the phenolate ion, or this anion here, has just one structure which can best be described as being at all times, no flipping back and forth, at all times a mixture or hybrid of all four of those structures. And the reason I always make such a big deal, I did this just today in my 227 classes also, if that makes you feel any better. But the reason I always stress that is because that notion is very difficult and opaque to our brains. I'm not really sure why. And I'm the same, by the way. I'm not kidding around when I say that I always make a big deal out of this to remind myself of it as well. I'm not just being cute. I really mean that, because it's a difficult idea. And so what that means is, let's now compare that conjugate base to its conjugate acid, which is, of course, just plain phenol. Well, that didn't turn out so well. Of course, this is the conjugate base of this species. This is the conjugate acid of that species. And what this is telling us is, if phenol gives up H+ and makes this anion, you get a very well stabilized conjugate base. It's stabilized by resonance. That minus charge isn't just sitting on the oxygen, but 3 of the carbon atoms in the aromatic ring help to share that minus charge. You can say the minus charge is delocalized. It's partly on the oxygen and partly distributed through the benzene ring. And anything you can do to delocalize a charge like that is going to make the species more stable, other things being equal, right? Because electrons are all negatively charged and like charges repel. And if you can spread out the minus charge over the molecule, then you're going to get a much more stable situation. And that's exactly what we see over here. So that's why phenol so readily gives up that proton. So much so that it's 1,000,000 times more acidic than water, or maybe even a little more than that more acidic than an aliphatic alcohol. If you compare, maybe I won't use methanol, let's use ethanol, just so that I'm not always using the same molecule. If you compare phenol to ethanol, and the phenolate ion to the ethoxide ion, which is the conjugate base of ethanol. And by the way, I don't care if you memorize those names also. If you want to just call this stuff CH3CH2O-, I'm fine with that. But it does have a name. It's called the ethoxide ion. Anyway, if you compare this situation to this one, in the case of this conjugate base of this species, in this compound, the minus charge is localized on the oxygen. It's not spread out anywhere. That's not a resonance stabilized species. Now, granted, oxygen is certainly not at all the worst atom to put a minus charge on. Oxygen is very electronegative. And so that's why you would expect to find, and you would find, that an alcohol, other things being equal, is considerably more acidic than an amine, because nitrogen is less electronegative than oxygen. Or you could even go in the other direction. Think how much more acidic HCl is. Well, or wait a minute, we're in the first row. So I guess you'd even have to say HF, which is a fairly weak acid, but way stronger than an alcohol or water. So I recall its pKa is like 4 or something like that. One could look it up. But be that as it may, to go back to my former point, here in this conjugate base of ethanol, the minus charge is localized in the oxygen, whereas here the minus charge is delocalized. It's spread out over the oxygen and 3 of the 6 carbons in the aromatic ring. So no wonder phenol is that much more willing to give up its proton than an aliphatic alcohol like ethanol. Actually, I think I have that pKa over here, 15.9. I have it in the class notes. I don't expect you guys to memorize it. So very nearly the same as water. And this principle doesn't just apply to, let me look at my time, resonance. The principle behind this, and this is all in the class notes. I hate to say I'm almost using my class notes as lecture notes here. Not almost, actually, that is what I'm doing. But just so you know that it is in the class notes. But the principle is that anything that you can do to a conjugate acid, to a conjugate base to stabilize it, other things being equal, will make the conjugate acid of that conjugate base stronger. So that's why phenol is a stronger acid than ethanol by, again, roughly a factor of 1,000,000. It's because the conjugate base of phenol is much more stable than the conjugate base of ethanol is. And again, ethanol, the ethoxide ion isn't bad. As anions go, this is a pretty good one. At least the minus charge is in a fairly electronegative atom. No, let me rephrase that, on a very electronegative atom. So it's got that. But here the minus charge is localized. Here it's delocalized. But there's other things that can help to delocalize negative charge. I compared in the class notes, and the reason I wanted to bring this up in particular is I actually think I got the name a little bit wrong. I compared it to something that in the class notes I called trifluoroethanol. But if you really wanted to be picky, I should call this 2,2,2 trifluoroethanol. I think the 1 carbon will have the OH on it, and the 3 fluorines are on carbon 2. So I think we really should call that 2,2,2 trifluoroethanol. So it's not a big deal, but I at least want my notes to be correct. So I'm going to try to remember to go make that correction and put up a new set of chapter 7 class notes. The pK of this guy is again significantly less, not quite as low as that of phenol, but I did write it down in your class notes. It's 12.4. So it's a little over 3 orders of magnitude, or 1,000 times more acidic than ethanol. And the reason is we've got these super electronegative fluorine atoms. And so if you take a look at the conjugate base of this species, it looks at first blush just like the conjugate base of regular ethanol without the fluorines, but there's more than meets the eye going on here. Because in this species, yes, you have a full minus charge, and yes, it's localized on this oxygen, but right nearby over here, right next door, you've got a carbon with 3 fluorine atoms, and those things are sucking electron density like mad. Fluorine's the most electronegative element there is. So in so doing, by withdrawing electron density away from the oxygen, it's helping the species to stabilize that minus charge, much more so than over here where we have just hydrogens. So no wonder this alcohol is about 1,000 times more acidic than that one. And I mention all this because I think you're going to find yourself having to make arguments of this type in the OWL assignment, for instance. It's just a good thing to be aware of. Whenever you're comparing acids, you want to look at their conjugate bases. And anything you see in comparing them that makes the conjugate base of one of them more stable than the other, assuming you're otherwise comparing apples to apples. So this is all other things being equal. But any phenomenon you can see that will stabilize significantly one of the conjugate bases over the other will make that conjugate acid stronger. And it makes sense. If you stabilize the conjugate base, then the conjugate acid wants to give up a proton that much more. So again, I'd rather you not just memorize these sentences I'm saying. They make sense if you think them through. It's a fairly sensible idea. Good. I think I also mentioned, I also mentioned thiols, and I think you can just read, I pointed out why thiols also are more acidic than alcohols. Again, other things being equal by about a factor of 1,000,000. In that case, the phenomenon in question is atomic size. You've got the minus charge on this relatively small oxygen atom, versus if we change that oxygen to a sulfur. Sulfur is now this big fat atom, right? So you're spreading out the minus charge over a larger surface area, effectively. So no wonder the thiol is going to be a stronger acid. It's going to want to give up H plus much more so than an alcohol will. So it's a similar argument, it's just a different phenomenon. But anything you can do to stabilize that minus charge is going to make the conjugate acid that much stronger. And again, I don't really care if you memorize any particular numbers. But I think you'll find in cases, even when you are given the numbers, that you can make some sense of it by using phenomena kind of like unto this. Reef, yes. Well, please register your attendance because we're not doing a Reef polling session today. But I think I do have. Yeah, in fact, I'm sure of it that I have a little exercise for you. I just want to point out one more thing, which is that alcohols, as I said, are amphoteric. That means that that they can also act as bases, which means just like water, if let's say we took our friend ethanol here, just as if you add a strong acid to water, you get H3O plus, the corresponding thing happens to alcohols. So if we added some, let's say, sulfuric acid, keeping it fairly dilute, amphoteric means can act as either an acid or a base. And you spelled it correctly. I have that word in the class notes also. So water is your classic amphoteric compound. It can act as an acid and give up an H plus and make OH minus, or it can act as a base and take on another H plus and make H3O plus. So alcohols can do the exact same thing. And small wonder, they're very similar to water. They're just organic derivatives of water. All you've done is taken one of the hydrogens in water and replaced with an alkyl group. So I would expect you would get the conjugate acid of ethanol, which would be CH3CH2 OH2 plus. This corresponds to H3O plus. And again, all we've done is swapped out one of the hydrogens in water for an ethyl group. And of course, you would also get the conjugate base of sulfuric acid, which is the bisulfate ion, HSO4 minus. So that equilibrium, I'm not even going to write an equilibrium. It would lie very heavily towards the right here. So just a reminder that alcohols are amphoteric, just like water is. Good, and I think that's probably enough for today. I don't feel like rushing, as I've said. I feel like I have more time this term. I feel like I've spread it out more than again, I didn't really know what really would have happened last term because it all went online all of a sudden. But I'm not going to push this any further than we really need to. I think that's enough for today. Good, so we have 5 minutes left. And I'll be honest, I think we did this exact thing on Friday, but it bears repeating. What is happening? I said to share the PowerPoint. Slideshow. I am not confident that you guys in chat can see it. You should be able to. Can you guys see the PowerPoint? Oh, good, very good. So we did something like this the other day, and this is really review from chapter 6. Let's take a secondary halide, and let's suppose that we have an enantiomerically pure R2-bromopentane, which I've shown. And let's say that we heated an ethanol. And let's suppose that the mechanism is Well, actually, let's do SN1 first, since I think that's the way we learned it. And then let's contemplate what the difference would be in the product if it went by SN2 instead. And I'll be honest, you will probably get some of each. Some of both will probably be happening here. But let's consider the two cases separately. So first, in other words, we've got a chiral carbon over here. How is the stereochemistry of this carbon going to compare to the starting material? This is pure R. So what would that look like after an SN1 reaction? And then what would it look like after an SN2 reaction? Some good review from chapter 6. And then we'll call it a day. I'm just looking at my phone for, I'm just using it as a clock. I promise I'm not playing Candy Crush or whatever people play. Well, you're not going to see it on Reef. No, oh, I'm sorry. I shouldn't say, ignore, please press A. Just register your attendance. And you won't see this on your Reef app because this is not for polling. Don't actually press A. No, my fault. Sorry about that. That's how I did it when we used clickers. So yeah, so you won't see this on your app. Just look at the screen. I'm playing Among Us, how? Still have yet to try that. Well, I guess I'd have to buy it probably. Gosh, everyone and their friend is playing that on Twitch though. My goodness, I really should watch that for a little while so I see what it's about. Oh, it is really? Huh. She says it's free on mobile. You should be able to see the question on the screen. So not on your Reef app, but you should be able to see it on the screen. Hopefully. But now 1 and 2 months ago, everyone and their friend, what was this game they were playing? Fall Guys. Oh my gosh. Everybody was playing that. There's no session to join, just register your attendance. As long as you've registered yourself as present, you are good to go. And like I said, candidly, I think we did this on Friday, but that's okay, bears repeating. Well, time is running out, so I already put in the answer since there's no harm in doing so. It's just attendance. And by the way, this is also already on eCampus. So, oh, I forgot to make that subscript. Oh, well, I'll fix that later. But remember that with an SN2 reaction, you will get complete inversion of configuration, right? So if the reacting carbon, if the carbon with the leaving group on it is chiral, you'll get the opposite chirality. And I would not expect you to be able to tell if this is R, but if you're told that this is R, then in the product, we would expect it to be S. That's if the reaction is SN2. In the case of an SN1 reaction, you'll get both. And in principle, we would expect to see a mixture. In theory, it should be a 50-50 mixture, because when the ethanol molecule comes in, after we get our carbocation, that carbocation's planar, right? And so the ethanol can then come in either from the front of the molecule or from behind. And there's no particular reason why it would prefer one over the other. Actually, that's kind of a lie, but it's close enough. So it's close. It's a close enough simplification. So you would see in principle both. Now, honestly, between you, me, and the wall, since this substrate is secondary, I bet in real life you would get both. And I would not be shocked if you got something that had a little bit more S than R. I would not be shocked if it was not exactly a racemic mixture. I wouldn't ask you to speculate on any of this. I'm just letting you know in case you're curious. But I wouldn't be shocked if it were 40-60, 35-65. How is the SN1 reaction possible? Well, because you could still get a carbocation, it just would be a secondary carbocation, which is less stable. But I do think you would get some SN2 and some SN1. And like I said, I don't care if you can actually speculate on the amount you would get of each. But if we actually ran this experiment, since we would get, I would expect us to get both, and I would expect the S compound to be favored. I wouldn't be shocked if it were 40-60 or 35-65. That's just a guess, but that's what I would guess. Good, so I think I'm out of time. Yep, I am. So we'll start with reactions of alcohols on Wednesday. Other than that, have a great day.